After configuring PyTorch in session 30, in this 30-second session, let us understand clearly the purpose of PyTorch, wheel and CUDA. Running modern generative AI models requires executing millions of complex matrix multiplications simultaneously. To run these tools locally, you process billions of calculations every second. A standard processing unit or CPU executes tasks sequentially, one after another. If you feed a massive neural network through a CPU, generating a response from a single prompt would take minutes or even hours. To bypass that bottleneck, we use PyTorch and NVIDIA's CUDA. PyTorch structures the deep learning math and CUDA acts as the software bridge, pushing all of those simultaneous calculations straight into the thousands of parallel processing cores inside your graphic card. By the end of this guide, you will build and verify a clean PyTorch environment specifically configured to run on newer RTX 40 and 50 series GPUs. Before we begin, we need two things already installed: Anaconda to manage your Python environments and the latest NVIDIA Studio drivers. Running advanced AI models entirely on your own hardware requires this specific software to hardware connection. Without it, the computing workload is impossible. Open your Anaconda prompt and type NVIDIA-SMI. This terminal readout clearly displays your hardware's current status, including your driver version and your CUDA version. You might notice the CUDA version listed here is something like 13.2, but the PyTorch command says 12.8. That is completely normal and they do not need to match exactly. The NVIDIA-SMI readout simply shows the maximum CUDA capability your installed NVIDIA driver can support. PyTorch bundles its own specific CUDA runtime libraries internally when it installs, so it just needs your system's driver to be new enough to handle the connection. Next, we create a new CUDA environment to isolate our workspace. Type Conda space create space -n torch _ GPU space Python equals 3.10 space -y. Once that finishes, type Conda space activate space torch _ GPU. Press enter, look at the left side of your command line. The prompt should now begin with torch _ GPU. This visual confirmation ensures you are safely inside the right environment and have not accidentally stayed in your base system. Keeping your Python environments isolated prevents different software dependencies from clashing, giving you a clean room for your AI development. Now we install the software. Enter the official PyTorch command: pip install torch, torch vision, torch audio, followed by the index URL, targeting the stable CUDA 12.8 or 13. This diagram compares compiling raw code against installing a Python wheel. Downloading a wheel is like grabbing an IKEA flat pack. You bypass manual compiling. This specific wheel already contains millions of pre-compiled C++ and GPU instructions. It drops straight into your system ready to work. If you are running an RTX 40 series card, that command usually executes flawlessly. But if you have a newer version RTX 50 series card built on the Blackwell architecture, you might hit a wall. You will know the stable build failed if you get an error stating your card has CUDA capability SM120 and is not compatible. If you hit that error, uninstall the broken version by typing pip uninstall torch -y. Then run the nightly build, which adds -pre to grab the pre-release version of the CUDA wheel designed specifically to handle the newer hardware. But now CUDA 12.8 and 13th PyTorch versions completely supports Blackwell 50 GPUs. Selecting the right precompiled architecture saves you from trying to compile the raw source code yourself, preventing system errors and manual troubleshooting. Just checking if your installation works by running a basic script that prints CUDA available true is insufficient. It proves Python can see the card, but it doesn't prove it can compute data. To guarantee PyTorch is actively executing math on your hardware, we force it to calculate random data using a matrix multiplication stress test. This visual compares our two test grids. With a 16 GB RTX 5070 Ti desktop card, you can generate a massive 5000 into 5000 matrix. For an 8 GB RTX 4060 laptop, we scaled that down to a 3000 into 3000 matrix to avoid running out of memory. Run the one-line Python command matching your hardware. If it works, the terminal will output the exact dimensions of the matrix it just calculated, followed by a passed message. To track your environment's performance over time, open Notepad, paste the diagnostic code block provided in the documentation and save it as the file check.torchgpu.py. Execute this new script from your terminal. Scan the readout to verify your GPU name identifies your card, your compute capability aligns with your hardware generation, and ensure your total VRAM registers correctly. Forcing the hardware to execute raw math is the only way to verify that your system is fully prepared to ingest massive AI workloads. Seeing that final GPU compute test passed message in your terminal means the software to hardware bridge is fully operational. You now possess an isolated GPU environment ready for production and a diagnostic tool to verify system health anytime you update your drivers. Now we put it to work. In the next step, we will use this exact environment to install faster Whisper for high-speed local audio transcription. Mastering the execution layer is the first requirement for taking total control of your complete AI setup.